Hey, everybody. Today we're going to talk about privacy attacks on machine learning and AI systems. And this is a bit of a follow up on how we address the problem of memorization and especially potential memorization of sensitive data in deep learning. And so if you're just catching up, you can click the link and watch the other parts of the series. But let's dive in today to privacy attacks. And specifically, we want to define what we're worried about. So if we realize that memorization is happening, or if we're worried that maybe we're saving potentially sensitive information in our machine learning model or our AI model, then we need to figure out like what actually does that look like in the real world? Is there a threat here? And then can we test for it? Can we do something to intervene? So before we talk about what we're going to do to intervene, we need to actually define what we're trying to reduce the chance of in a more measurable manner. For example, perhaps somebody donates their data or their data is used to classify sexually transmitted diseases or to potentially predict medicines to help sexually transmitted diseases. Maybe by doing something with the model, I can figure out that Peter, imaginary person, has a STD, right? That could be one problem. Another problem could be I'm an artist. I'm using generative AI. I think I'm using a sample that is truly unique because it comes from my prompt or whatever it is. And find out later when I get sued, oh, actually, that's so and so's sample and it just wasn't officially cited. And then finally, we have kind of a larger privacy violation, again, is potentially using somebody's face without knowing it or using somebody's likeness without knowing it, either intentionally or unintentionally. And if you're a machine learning person, I recommend you read this paper called This Person Probably Exists, which was one of the first to talk about the problem of image generation in deep learning networks, basically paraphrasing or using literally people's faces as part of the output. So these are all things that we're maybe worried about. So how do we actually measure them? Well, there's two major types of attacks we're going to talk about today. And the first one is membership inference attacks. You might have heard about it, but I'm going to try to give you both an intuition and an understanding of these membership inference attacks. What happens is perhaps I'm going to go back to Peter. Perhaps I know I have some of Peter's data, or I know him, so I know some things about him. I can guess his data. Or maybe I just start with my best guess and then I refine my attack over time. So these are all potential starting points. Then I put Peter's data into the model. Now, maybe I have the model locally, then I can see more. But even if I have just the API access, I just send it through the API to the model and I get back the inference. I get back the prediction from the model. This could be the next token. It could be the next pixel. It could be an entire, whatever it is, whatever the model's output is. And it could be this probability distribution, essentially, or prediction across several different classes, for example, if we're talking about classification model. And this is kind of the model's output. We're going to talk about it later as model's output. So whatever the model's output is, I get that, right? And what if I told you I could use that to infer, to figure out if Peter's data was in the training data or not? And because I can do this, if the model is specific, let's say about disease patterns for STDs, then I know that Peter at some point in time had an STD, for example. So how does this actually work? Well, Carlini et al. Has a great paper that I highly recommend where they introduce the idea of a likelihood ratio attack, which is basically just a more specific type of membership inference attack. And what we're going to talk about is we're trying to take the model outputs and guess between who was in the training data, who wasn't. So member in the training data, non-member not in the training data. And already we can see here, this is from this paper, the right-hand column displays some outliers within their class. So some images that didn't look like the other images in their class. And here we can see Can we separate the red and the blue? Yes, we certainly can. So just using the model's outputs, and here they're using cross-entropy loss, which is essentially comparing the model outputs to what we think reality is, so to the labeled dog, to the labeled truck, and seeing essentially how much change would we have to have between what the model output and what dog should look like. So we can see here from those model outputs, they trained thousands of models. From those model outputs, we have this clear threshold that we could set and say, when the loss is above this much, then we know that it's not in the training data, for example. And then when we look to the left-hand column, we see inliers, so more common images, so not outlier images. And we see that when it's easy to fit, so when it's a simple class, like bird, and bird is learned easily, then it's very difficult to separate. It's basically impossible. The model outputs are overlapping. We cannot separate them. But when we look at the more complex examples, so airplane in this data set is harder to learn. It's a little bit, has more depth and complexity as a class. Then we can see, is it as easy as the outliers? No, but we can start to maybe, if it was on the edges, then we could perhaps predict. Not 100%, but perhaps. Okay, so this is our goal. This is our goal as an attacker. Now, how do we actually do that? We take some training data. Either we can use training data that we know the model has if we have it. If it's like trained on open data that we can just download and use, we can do that. If it's trained on private data, then we can try our best approximation of the training data. Then we split that training data into subsets. From those subsets, we train example target models. So we train perhaps many, perhaps few. Sometimes these are called shadow models, if you've heard of that. And they can be the same architecture as the target model, or they can just be another deep learning architecture that we think will transfer well. So it doesn't necessarily have to be the biggest model possible, can be smaller. And then we're going to collect those label outputs. Again, we're going to run through those inferences. We're going to try to store the members and the non-members by the model outputs or by the cross-entropy loss if we have actual real labels, which we probably do because we have the training data. We're going to collect those, and then we're going to see, can I do a simple threshold attack? Can I separate those distributions easily? If so, then that's maybe the simplest way. Or I can train a model to determine, based on the model outputs, was this in the training data or out of the training data? And this works. So the likelihood ratio attack from Carlini et al. Says that we should pin a false positive rate. So we should say, okay, we're going to try to hold the model. If we train a discriminator, we're going to hold it at a false positive rate that's very low. So we don't want to say that something is a member that's not actually a member. That weakens our attack vector. But this can then be used to determine, was this person's data or was this data, it doesn't have to be a person's data, was this data in the training data or not? And this can teach us something. So we can use this information, maybe based on the model, to infer something about the person or the people or the songs or books, right? Or we can use this to build more advanced attacks. And so if we can determine that something's in the training data, we can potentially also target it for data reconstruction or data exfiltration. So we want to try to get as close as possible copy of the training data out of the model. How does this work? Well, here I am. I already ran my MIA, my membership inference attack, or maybe I didn't, and I'm just testing out exfiltration. That's fine. And here's some easy to think about prompting, right? So here I'm using a specific example of some sort of multimodal or LLM or text to image, where I might be saying, please finish this text, please draw me a picture, or please make me a photo, or what do you know? I can even start my query large. What do you know about this person? What do you know about this author, right? And each of these gives me either I know exactly what data I'm looking for, or I'm going to start my search broad and I'm going to hone down. So I could also start with like a fuzzy image and put it in and ask for classification and then improve my attack as we go. And then I put that into the model, right? If I have a local model, I can observe it. If I have an API only model, I can just collect the outputs. And essentially, my goal is to use those model outputs either for myself to reconstruct the data, so locally that I can reconstruct the data, or to actually pull the data out of the model via this process, right? And this is doable. This is actually, in some models, easier than one might think. So in this case, this was using the Midjourney commercially available product. And the images that you see on the left-hand side are from the training data. The images that you see on the right-hand side are from prompting the model with the training data text. So we see this is perhaps not a one-to-one, it's not an exact copy, but it's what the author of this paper, Ryan Webster, calls image paraphrasing. And so if we have an idea of the training data, or even if we don't have an idea of the training data, but we want to continuously probe the model to collect information and then use that to better center, focus, and hone our query, then we can slowly, for these, especially for these memorized points, we can slowly better our attack until we have a paraphrased version of the data or we have an exact copy of the data. And so what should we do? I'm curious of your thoughts. One thing that maybe we can start talking about and thinking about is if we're using personal data, if we're using sensitive data, we want maybe to get consent. We want people to say, you know what, I know and understand the risks, and I want you to use my data. I'm okay with my face being shown. I'm okay with this data being out there, right? And there's a lot of use cases where that would be true for many people. The other thing that we can do is we can start talking about the risks. And I mean this both within technical teams, within organizations, and also within our friends and family and people we know. Did you know that memorization can occur? Did you know that data can be extracted out of machine learning models? And talk about them and say, you know, what do you think should change or be different or the same? You could run MIAs. So there's ways to actually run MIAs on your infrastructure. I'll do more information on that coming soon. And you can test for memorization. So you can both target with MIAs and you can target with data exfiltration. There's also some other ways, clever ways to think through memorization while training. But these are all things you can do. And I'm curious, what do you think we should do with knowing these private attacks? What do you think would be an appropriate way to integrate this into how we do machine learning or how AI products are offered today? So stay tuned. I'll be excited to hear more.